But I don't understand that. I'm not studying. Anyway, in any case, he's going to lecture in English. I didn't have to worry about this exchange. And so, anyway, I'm very glad to have him here and lecture on network curvature and security applications. Thank you.
Thank you very much. Okay, what I'm going to be talking about is kind of outside beaten track, really. It's kind of a new aspect of security and propagation and networking. Well, I'm tapping into some very recent mathematics, a piece of mathematics called coarse geometry that has come up over the past 20 years, and that has been said to be the most significant development in geometry over the past 20 years. Okay, you know that network security, there has been a lot of traffic signal analysis in network security, using some statistical information of the signal to pick up when an intrusion or some illegal activity is happening. Okay, well, more fundamentally, the traffic signals are carried by a network. And the network could have different topologies, different graph theoretical properties. And what I'm saying is that we might have to come back to the more fundamental issue of what is the network topology, how it could influence security, propagation, and related things. Some of the things I'm going to be aiming at is some architectural issue. Some architecture are lending themselves quite easily to multipath routing, something that you might want to implement if one of the links might be compromised. Worm propagation, the way a worm is propagating depends heavily on the topology of the network. We would like to get some ideas as to what's going on there. Denial of service attack. What I'm going to show is that nodes of local strong negative curvature are very vulnerable to this kind of attack. So there is a lot of connection between some advanced mathematics and security in here. Okay, what I'm going to be showing is that the curvature of the network is of paramount importance in many issues related to security, propagation, etc., etc. Now, what is the graph curvature? Well, the problem is that curvature is usually something that applies to Riemannian manifold. I'm going to show that it's a concept that can be applied to graph. So, once we have that concept of curvature of a graph, then my point is that all of the topological properties of the graph are encapsulated in that curvature concept. That's what I'm going to show. And the issue is going to be negatively curved versus positively curved network. And I'm going to show that there is a big difference that has a lot of implication. Okay, somehow, what is a negatively curved network? Well, it's a core-concentric network. You know the power law. See, that has been very popular. And that power law, I'm going to say, well, we could reformulate it more geometrically in terms of curvature, in terms of negative curvature. Positive curvature, that's rather the small wall graph. Again, we are back to traditional ideas like core-concentric heavy tail versus small wall. And I'm going to show that, again, it's a matter of the curvature, that these kind of small wall graphs have positive curvature. And there are many other materialization of that positive curvature versus negative curvature dichotomy. Okay, let us try to understand the concept of graph curvature. I have been trying to summarize a little bit what curvature is in the Riemannian manifold setup. Okay, you know Euclidean geometry. I don't have to repeat high school geometry. Well, actually, I'm going through this with my daughter now. Anyway, you know the story. The sum of the internal angles amounts to pi. In a hyperbolic manifold, like a saddle, if you have 3 points A, B, and C, and if you join them by minimum length path geodesics, somehow you are going to see, and it's basic in Riemannian geometry, that the sum of the angles is less than pi. Meaning that the triangle is thin. Okay, meaning that the triangle is thin. The thinness of the triangle you can easily quantify by the gap between pi and the sum of the internal angles. The problem is that that's okay for a Riemannian manifold because you have an inner product, hence you have angles. But, I mean, on a graph, you do not have angles. So the issue is, well, we're just going to have to try to find some metric reformulation of this thinness. Somehow, using the fact that the graph is a metric space, could we reformulate that thinness using purely metric space concept? The answer is yes, we can do that, and that's what we are going to do, really. Okay, and then positive curvature. Well, in a positively curvature space like a sphere, the sum of the angles is larger than pi, and somehow the triangles are looking fatter than the Euclidean triangle. Okay, and somehow what we are going to try to do is to translate that thing there, because negative curvature is really the most important, at least is the mathematically best developed theory. I'm going to try to translate that thinness into the metric space concept. Okay, just to give you a little bit of an idea how thin triangles are naturally coming up in network, this is the ISP graph, Internet Service Provider graph. So every node is an ISP, every node is an ISP, and every link, that's some kind of communication among the ISP or the autonomous system that the border gateway protocol would reveal. Okay, now, take 3 points at the periphery there, A, B, C, join them with minimum communication cost path, and you're going to see that you have to transit via the core. Okay, you have to transit via the core so that this triangle is thin. Well, not in the angle concept, because somehow we do not have angles. Well, at least I'll show you that we can define the concept of angle, except that is not trivial. But by visual inspection, we see that that triangle is thin. Okay, so that definitely the Internet Service Provider graph is a hyperbolic graph of negative curvature because the geodesic triangles are thin. There are many other examples, really. Okay, this is the Walt graph, and again we see those very, very connected cores there, again giving that whole graph a negative curvature property. Something a little bit for the fun in here. For the fun, I talked about the positive curvature versus negative curvature dichotomy, and I claim that's the same as the Airbus A380 versus the competitor, the Boeing 777. Well, there's an interesting concept in here. Boeing hopes airlines will use it to open new non-stop link between mid-sized cities. So somehow this aircraft is designed to fly on a graph that does not have the big hubs like Los Angeles or Washington, D.C. On the other hand, the A380, the Airbus, the big Airbus, has an airport compatibility problem. So that one is meant to fly on some of these core concentric graphs. It's an interesting story because, to my knowledge, it's the very first time an airline, an aircraft company is designing an aircraft with some ideas as to the graph is going to fly on. Now let us look at the route maps now. Okay, this is the route map of American Airlines. You see these big hub, core concentric graph. The route map is core concentric. Now, an interesting story is that if you go to the website of Southwest Airlines, you know Southwest Airlines has been a success story, business venture, totally outside business. You do not see these big hubs. It's more like a constant degree graph, a meshed network that has negative curvature. This one has positive curvature. Just a fun illustration. Okay, we could go even further, talk about biology. This is the protein interaction network of a yeast. Okay, somehow the nodes are protein, and the connections there, the connections are hydrogen bonds, physiologically relevant bonds. Again, look, this is core concentric, so it's a negative curvature graph because I could do the same exercise as I did before. I could take a B there, a C there, and you would have to transit through the core. Okay, so there is definitely something going on there. Okay, so I gave you a bit of the ideas. Now we have to start formalizing that whole thing. And the problem is that curvature has been defined for Riemannian manifold. It's an ironclad concept. The problem is that if we apply it to graph, it's getting a bit more difficult, and there is no easy, uniform way to do it, unfortunately. The first thing you are going to bang your head on is that you'll have to make a difference between large-scale curvature and small-scale curvature. There's just no way to have like a unifying, all-encompassing concept. No, large-scale networks are rather negatively curved, and maybe it's something I kind of missed a little bit in a few transparencies before, right here, because negative curvature and positively curved manifold have infinite diameter. Positively curved has a finite diameter. So whenever it comes to very large-scale problems, the natural curvature concept is negative. Small scale, in general, we are going to be dealing with positive curvature, although we could not exclude negative curvature as well. Where I'm going to is the following. Many networks are negatively curved in the large scale with local patches of positive curvature. And in fact, some people in Switzerland have shown that the local curvature is behaving wild, and I'll come to that. There is a mathematical problem called the obstruction to smoothing the curvature. Okay, how are we going to really define the curvature of a graph? Well, there are several approaches. Basically, these two columns in here are based, okay, that first column, let me just put it this way, are based on the idea of comparison. That's what I was trying to give you the intuition of. You look at the way a triangle is coming on a saddle on a negatively curved surface, and then you look at the communication path on the ISP graph. You compare and you see the same behavior, the same metric behavior. So comparison theory is the following idea. Look at the Riemannian manifold, look at how things are behaving metrically, because you do not have a metric concept on you don't have an inner product on the graph. On the graph you have a metric concept, on the Riemannian manifold you have a metric concept, but really you have to try to look at the Riemann manifold, the behavior of the geodesic and the triangle, and say, okay, metrically what is going on? And if metrically I have the same story on a graph, then I would say that the graph has negative or positive curvature. That's the idea of the first column there. Okay, another idea that we have applied that was reasonably well, but that is computational, well, it's not that difficult really. It's isometric embedding, meaning that you have a graph, and if you find an embedding of that graph in a Riemannian manifold of curvature kappa, then you could say that the graph is naturally acquiring the curvature of the manifold. And then we are getting into gram matrices, nothing very difficult there. Okay, another thing is that there is an established theory of embedding graph on surfaces. The surface could have a certain number of handles. The general theorem is saying that any graph can be embedded without link crossing on a sphere with a certain amount of handles. The number of handles is called the genius of the graph. And that's what we are going to do, except that the mapping is not isometric in this case, and then we have to fix up the curvature. But this is the gateway to lots of pretty strong topology in here. Okay, so the problem is that, you see, there is no linear road map in here. I'll have to navigate through these two-dimensional graph table, I should rather say, going from one thing to another, but every time I'm going to go to a new approach, I'll show you exactly where I am in this matrix. Now, the other thing is that this is the mathematics, and I can really map that matrix to security problems. There we go. Okay. So the comparison theory. See, the comparison theory at the large scale, this is the issue of multi-path, like many different paths to communicate between the same pair of points. Yes?
Sorry, before you move to this, may I ask if that embedding, is that well defined?
Yes.
How do you do it?
I'll show you.
I would imagine there can be many versions of the embedding, and then the curvature would vary. How do you fix the curvature exactly?
Because sometimes you can only do the embedding in a fixed curvature. I have some very specific examples about that.
Okay, and then when you're speaking of isometric or non-isometric embeddings, the metric on a graph, is it just the number of edges from a vertex to a vertex?
It could be anything. You could give yourself any weight on the link. You could have the number of hops,
Sure.
or you could have the link weight.
Sure, and why does it happen that an embedding, let's say, if we take a planar graph, put it on a sphere like genus 0, why is that non-isometric?
This one.
Yeah.
It need not be isometric in here. In here, it's another kind of approach to try to get to some small scale versus large scale topology. And what I'm doing, initially the embedding is not isometric, then I'm fixing the curvature locally, using some faults and some cones to fix it up. Yeah. But in the large scale, I'm still okay.
Yes.
Okay, you got it. Okay. So we were, sorry. Okay. So, Schill, in the large scale, the comparison theory is going to lead to some issues like multi-path, warm propagation, it's a large scale phenomenon, you agree with me, and stability of the network. Stability, it means that you are readjusting the link weight and you want to make sure that the geodesics, the communication paths, are not going to be flickering too much. And then you have sometimes this aberrant behavior, the flickering problems, where you see oscillation of the path. That's a lack of stability. I'm going to show that this is unlikely to happen on negative curvature. Okay, small scale, like a point that is vulnerable to denial of service attack. That's because of a local negative curvature. So what I'm going to do again is to follow also this matrix with the security application. And I think we are ready to start, and I'm going to start with probably the most straightforward part of the talk, the one that applies more easily. It's a large-scale analysis. The curvature is negative, and it's based on the comparison theory. And this is like the concept of delta hyperbolic space, which is due to Gromov. The delta, it's kind of, the delta, it's kind of the radius of that inner circle there that is supposed to be small. It's kind of related to the side of the inscribed circle, and in negative curvature that is small. So that's what I'm going to explain. And again, the comparison theory is what is going on the Riemannian manifold. Metrically, what is going on in negatively curved Riemannian manifold, and then translate that to metric space. Well, on the Riemannian manifold, you have the following remarkable metric property. Take three vertices A, B, C, join them with minimum length path, and then take points X, Z, and Y on the edges, the blue points, and try to make the perimeter of X, Y, Z as small as possible. There we go. It turns out that no matter how spread the A, B, and C points are, this blue triangle has its perimeter bounded by the curvature. This is metrically something that is happening in a Riemannian manifold. And then I'm going to say, okay, if this is happening on the graph, I'm going to say that the graph is large scale hyperbolic or delta hyperbolic. And here it is. No, we are on graph.
What is the kappa m there?
The maximum. Okay. Because in here, okay, there we go.
Okay.
So I don't need a space of constant curvature. The curvature has to be bounded from above. Okay? All right. Okay, so no, I am on graphs now, and I have three vertices A, B, and C. These are the minimum communication cost path. It could be the minimum number of hops if you want. And I'm picking up points X, Y, and Z. Okay, trying to find the minimum perimeter for the blue triangle for any black triangle. There it is. Okay, and then I'm saying that the graph is delta hyperbolic is no matter how distance A, B, and C are, this is remaining bounded. Okay, and there are lots of computational things. You could see that all of these infima and suprema are reached on the vertices, nothing big. Okay, so this would be the concept of a delta hyperbolic graph, basically mapping Riemannian geometry to graph. There it is. Now, there is a problem with this. There is a problem with it. The problem is that I'm only asking the delta, that is the perimeter of that blue triangle, to be finite. Okay, well, ISP network graphs are huge, but they are finite. Okay, then how small is small for the delta? This definition somehow would go for any graph, really. Okay, that's where engineers are getting into the picture. Mathematicians would say, okay, that's what we have done theoretically. How small the delta should be, it's up to you engineers to find that. Okay.
It doesn't have a notion of scale still.
I'm coming to the notion of scale. Okay, that's the problem. I have to, because delta has to be scaled. You are right. Delta should be scaled relative to the diameter of the whole network. I'm coming to this. I'm giving you a little bit of more feeling as to what delta hyperbolic is. Okay, this is a tree. And then you could easily see that for a tree on a tree, any triangle would have delta is equal to 0. Okay, if you have just a small triangle there, it's not that hard to see that the delta is equal to 2, just to give a little bit of an idea as to what's going on there. Okay, then I'm getting to the point of scaling now. So as I was saying, we are dealing with finite graphs. It's not good enough to say that delta is finite. It has to be small relative to something. And as Dr. Barras was saying, well, it looks like in engineering reasonable to scale the delta, the perimeter of that inscribed triangle, relative to the diameter of the whole thing. And again, the ideas go back to Riemannian geometry. Use the comparison ID, see what's happening in Riemannian geometry, see what's happening for a negatively curved Riemannian manifold, look at what's happening over a Euclidean space, look at what's happening over a spherical space, a positively curved space. And then you see that in here you have to bound the diameter of this triangle by epsilon, because somehow this maximization naturally has a tendency to make the triangle very small, so that you would be actually in the tangent space, and in the tangent space you are back to Euclidean geometry. So you have to give a bound on the diameter of this triangle, but you know, on a network you just cannot have an infinitesimally small triangle. Okay, so that's perfectly justifiable. And then you see that in negative curvature, the maximum that you could possibly reach is bounded by the maximum that you could possibly reach in Euclidean space, which is 3/2. I'm going to show how that happened. And then you see that in positive curvature, you are bounded from below by the 3/2. Okay, so it looks like if you look at delta divided by diameter for the three different space, 3/2 is the threshold. So that this would be like the definition of hyperbolic. And by the same token, I'm already coming up with some definition of positive curvature, that somehow this ratio has to be larger than 3/2.
So the diameter condition, positive case, within the max is going the other way.
That's right, that's right.
Yeah, well, can you sort of give me a little bit of intuition on that?
Okay, think about a sphere. Think about drawing a geodesic triangle on a sphere. As you could see, the larger the triangle, the fatter it's going to be. Okay, because, okay, so to really reach this maximum in here, you have to take big triangles, because on the sphere, the bigger the triangle, the fatter they are. And it goes the opposite way on the hyperbolic manifold, because to have a small delta, you need a small triangle, and then that's the reason why you have to bound it. Do you see the intuition? Okay, good. All right. Here is the proof that, okay, this is the intuition. The intuition in Euclidean geometry that the purple triangle is the fattest, that the equilateral triangle is the fattest triangle, and somehow the optimal is the blue one, and that is the proof based on some Tarski-Seidenberg stuff, but let me skip this. Okay, good. Let us come now to trying to apply that delta divided by diameter concept to some real network graphs. Okay. What I'm going to do in here, is to try to link the delta divided by diameter to that well-known heavy tail property. Okay, the fact that a network, at least like the network the way it is, has some big hubs. the kind of big hubs that you have in the road map of the major airlines. Just as a joke, you might ask me, what has that to do with security, big hubs and roadmap of airline? I'm just going to tell you that prior to September the 11th, when I was teaching classes on networks, we were going on the web and looking at the roadmap of all of these airlines. After September the 11th, they were just taking out of the web. That's the reason why I have such a lousy picture of the American airline roadmap. I won't comment on the way I got the Southwest Airlines. That was a little bit like cheating anyway. Okay, so what I'm going to do in here is take those heavy tail network, and there has been an algorithm that was proposed that was a model of the build-up of the internet that was leading to the infinite variance property of the degree called the heavy tail, or called the power law. And it's kind of a model that is accepted to lead to graphs that compare well with real network graph. And what I'm going to show is that indeed that generator, the scale-free generator, is leading to delta divided by diameter is equal to 3/2. Okay, this is that model of the build-up of the internet. The idea is that you start initially with a core network there. Okay, a small number of nodes link in some way, and we try to ring, line, star to begin with, trees actually. And then you add the first node, and somehow you want, that the first node really you don't know exactly how to connect it, because somehow the connectivity of all of the core nodes at the first stage is the same. But anyway, you make a choice. There we go. At the second extra node that you are adding, then you see that you want node number 2 to have an immediate gateway to the rest of the network, and you would preferentially attach it to those points that are already heavily connected. The rich are getting richer. Okay, that's the preferential attachment issue. And like that, you built up the network. You built it up, and it can be shown.
The differential here is because the experience of people is that if I do that, I get faster response versus going to 2 hops. Is that?
That's right. Yeah, exactly. That's the rationale. No,
if I get a different setup, it may change.
It may change. Yes.
Go to one and then
yes.
How about congestion? I mean, if you add more and more links on the same hub, it might be congested, just like the cities, right? So how does that preferential thing work?
Preferential things means that you link number 2 with a probability that is proportional to the already existing degree of the nodes.
Right.
That's a preferential attachment. We also tried uniform attachment. I'm going to show the result there. That a uniform attachment.
This is actually how it's done now. And the explanation on the behavioral side is that people go to these nodes because they have bigger servers, more servers.
You have.
If that changes, that will change.
Yeah.
Okay. Now, another thing is that there is also a very similar model to the yeast evolution. That's another interesting thing. Okay. So what we did, we start up with a certain number of nodes, and we simulated all the way to 40 iteration. And what we did is that we looked at the geodesic triangle of the scale-free graphs. And we did it very conservatively, because we really took the maximum, whereas we would like the delta to be divided by diameter to be small. Okay, and then we took the mathematical expectation of that over the scale-free generator, and this is the result. Okay, this is the result. Okay.
What were the embedding space in your simulations?
It's not quite the embedding approach. Nevertheless, the idea is to you might say that you have an approximate embedding in the large scale. It's not quite the embedding theory, it's the comparison theory. Compare metric properties on the Riemannian manifold with what you could get on the graph. Okay, it's some kind of an approximate large scale embedding. Okay, so this is the result. This is the result. So, this is the total number of edges Okay, that's a little bit tricky because we had to adjust that parameter, the total number of edges, related to all of the parameters I have to set up in the previous slide. This is the delta divided by diameter there. That's the Euclidean threshold 1.5. And then what you can see is that you start definitely with something that is looking hyperbolic. And you go to something that is looking like spherical because it's above the threshold of 1.5. Okay, somehow what's happening is that here you have graphs that are very close to trees, not very interesting really, because we started up with a tree-like network, and then initially the way the algorithm is coming up, you are not too far to trees, so that this is not very interesting. Nor is this interesting because somehow the graph is becoming overlinked, it's getting close to the complete graph. The interesting region is right there. And you see that if you set up the parameter of the scale-free generator properly, you're going to end up into this region. And which curve, by the same token, we tried the small wall graphs, we try the scale-free graph, we tried the purely random graph of Erdos and Renai. We also did the uniform attachment as a comparison. Look, among all of these curves, the red curve is the one that has the smallest delta divided by diameter, right? That's precisely the growth with preferential attachment, the scale-free generator. Okay, now which one is the...
This picture does not... Okay, coming back to the question that Sasha was asking. This picture I cannot change by changing how I do the embedding or how I do the calculation?
No.
Is the theorem of that? Because, I mean, if I change the metric, like the discussion we had with the other one back there, if I change my preferences,
okay,
I mean,
no,
right? I mean,
okay.
There are many ways to embed the graph into the manifold or do the calculation.
Okay.
What do you know about the?
All I know is that it's negatively curved in the large scale. That's all.
Okay.
That's all. I do not specify a curvature, a Riemannian curvature. I do not, but I'm saying that it's in the large scale.
But I mean, this, if I follow this graph is very telling, of course.
Mm-hmm.
But then, to what extent this graph depends on the metrics that I started? I mean, this graph, I mean, not the graph of the network. This line here, that it shows the story. How this depends on the metrics I choose? Does it? It doesn't.
What metric? What metric?
The metric on the graph.
Oh, okay. We just took the number of hops.
Okay.
Yeah.
What if I? Okay, that's good. What if I change it?
I don't know.
Okay.
I don't know.
This is hop count.
This is hop counting. Yes.
Right.
Okay. Yeah. Okay. All right.
It will change. It will change.
It would change. Yeah. It would change. Yeah. Yeah. But I think that somehow the scale-free generator is meant to be a hop-to-hop counting.
Because that's what their point is.
Exactly.
They just measure connectivity.
Exactly.
Am I connected to that?
Exactly. Yeah.
And that's definitely hop count.
No, that's something that is open. I could ask my postdoc to do this. Okay. Now let us look at the worst possible curve. Well, that one, the one that is the least hyperbolic is the small wall graph. Okay, there we are getting into small walls, we are getting to small diameters, and small diameters graph are rather positively curved. Okay, what I would like to justify then...
So it's true, right, that on this end, I have no loops. Mostly.
That's right. Roughly you have graphs, you have trees there, something
and
like...
I go up, I get more loops. I can go around the network.
You get almost like to the complete graph.
Right.
And that's what I'm going to show then. Okay? That somehow there we are going to the complete graph. For the complete graph, the delta divided by diameter is 2, and that we are talking about positive curvature. And by the same token, I'm going to do really the embedding there. Okay. So somehow for the complete graph, so where I'm going is right there to that region now. And for the complete graph now, I'm going to do the real embedding. Because it's a complete graph, it has small diameter, I can afford doing the real embedding. And I'm going to show how to use the gram matrix for this. Okay, here it is. All right, this is a complete graph. If you think a little bit about this, you pick any triangle, all of these triangles are the same, and if you look at the minimum perimeter inscribed triangle, actually 2 of the blue nodes are confused so that its delta is equal to 2. That explains why that curves goes to delta is equal to 2, because we are converging to the complete graph. Okay, and then the other thing I'd like to do now is to justify the fact that the complete graph, I do have an isometric embedding into a sphere, actually. The complete graph on n node, you can isometrically embed in a sphere of dimension n-2 with this radius. And then I'm using the graph matrix, the real embedding. Okay, what is happening? If you think about the graph, really, as far as communication is concerned, it's a set of vertices, okay, given by a set of distances. That's all you really need to care about. And it turns out that this graph, a set of nodes with a set of distances, is isometrically embeddable in the positively curved Riemannian manifold if this matrix, okay, you see this matrix is the cosine, the distance, the square root of the curvature. And the matrix is indexed by the index of the vertices. That matrix has to be positive definite. And you easily check this on the complete graph, and then you find that you can do the embedding in any, in general, on the sphere of dimension n-1 with this condition on the curvature. You could do it on a sphere of dimension n-2, as I said, but then you have an equality sign there. So for the complete graph, we are successfully at doing the real exact embedding. We don't have to argue a little bit more loosely on just negative curvature in the large scale. Okay. Now, in the large scale, somehow, that isometric embedding, I'm just trying to do the real embedding to a little bit answer your question. It turns out we just cannot do it exactly in the large scale. There are some little problems, but we could do it in some limiting sense. And that explains a little bit what I said. You do the approximate embedding in the large scale. Okay, here it is. Okay, let us do the following exercise. We have the ISP graph. We would like to show embeddability of that graph into some negatively curved space, and I'm building up a model. Okay, well, you know, the ISP graph, you have a very connected core and these long tangents, so the easiest possible graph model would be a complete graph, and then long tangents there of length L. And then what I can do is to write down explicitly the condition for explicit, exact isometric embedding and see what's going on. Okay, here is the condition. Now, instead of cosine, you have cosine hyperbolic for embeddability in a hyperbolic space. There we go. And that matrix must have some kind of combination of eigenvalues. Actually, somehow the principal minors must have alternate sign. And somehow you see that you are not quite holding that condition, but you are only holding this condition in some limiting sense. Either the length of the tendrils has to go to infinity, or the curvature has to go to infinity. That's what I mean by approximate embedding in a negative curvature in the large scale. Okay. All right. I'd like to talk a little bit about some security application of basically the delta hyperbolic property. You remember on the theoretical matrix that was the groom of the delta hyperbolic property. I'd like to talk a little bit about that. Stability means the following. It means the following. You have a graph. You have some weight on every link. Okay? And you have the network of geodesic. You take 2 points, a source and a destination, and for certain link weight, you do see a minimum communication cost path. Okay, so you change the link weight. Your path is going to change. Okay, now assume that you will do some adaptive networking. You see a link that is getting too much congested. You would like to reroute some traffic around other link. You increase the weight of that link. You go along another path, right? But some of these algorithms are leading to an instability. You see the minimum communication cost path flickering. That's a flickering problem. It's some kind of an aberrant behavior of the routing. That's what I call instability. Okay? What I claim is that this is not likely to happen in negative curvature, and I'll explain why. Okay? All right.
So shouldn't this be the case for multipath scenario?
Yes, yes. Yes, I'm coming to this. Yeah. Okay. Multipath scenario. Here it is. Okay, if a link is compromised, or you are not sure, you would like to send at least some of the packets around alternate path. But the problem is that if you send packet 1, 2, and 3 in a sequence from the source, and if some of the packets are taking some route, other packets another route, somehow the destination, the packets might be out of order. And you want that out of order to be kept minimum, because TCP is really not very good at reordering the packets. So if you want to do multipath routing, you do need alternate paths that have a cost close to the optimal one. And I claim this is happening in a delta hyperbolic space. Here it is. Okay, how do we do this? Okay, this is from A to B there. Okay, this is the nominal minimum communication cost path. Let us assume that we are worried about a link being compromised there, and you would like to send at least some packets along an alternate path, but the alternate path must have a cost close to the optimal one. This is the construction. You pick up a node C, you draw the geodesic triangle. Okay, then for that geodesic triangle, you just do the delta, and you get that blue triangle there. And then you could say, instead of sending all of the packets from A to B, you could reroute them from A to Y like this. Okay, well, this is what's happening. And again, this is justifying the delta divided by diameter as a quality factor of the network. I said that delta less than infinity, that's what mathematicians are doing, and I said that engineers are doing delta divided by diameter. And then you see that the relative error, which is kind of the length of the alternate path divided by the length of the optimal path, is bounded precisely by that delta divided by diameter. So I've been advertising for the delta divided by diameter to kind of tell us the hyperbolic property in the large scale when you have a network that is large but still finite. And then you do see very well that you keep under control the cost of the alternate path. And this is where stability is coming into play. It turns out that this alternate path is remaining close to the nominal one. And again, you have a bound, because the Hausdorff distance between the nominal path and the alternate one is less than or equal to delta divided by 2. So the small delta promotes stability somehow, because somehow the paths that are like that have a slightly different cost are remaining close. That only happening in negative curvature. In positive curvature is totally the other way, really. Because if you think about a sphere, if you think about communication path between the South Pole and a point around the North Pole, you see that the geodesic could go really berserk. Okay? So on a positively curved space, the behavior of the geodesic is not good. On a negative curvature space, the behavior of the geodesic is good. Okay. So that's a bit about multipath routing. Okay, worms. Let me explain a little bit about worm propagation. I think I'll try to be a little bit faster here, because I'd like to come to some theorem. Okay, these are some propagation curve of worms, but I'd like to come to the following results in here. Okay, let me just come to this. Actually, the way I like to see worm propagation, especially worm propagation through the mail server, is to view the servers, the router, as kind of a big network, and the mail server to be some kind of a local feedback. Of course, this local feedback is extremely hard to model, because it depends a little bit, like you get a message, how likely are you to respond, but you can imagine conceptually a feedback there. Okay. You know that during the big attacks, like 2 summers ago, you were getting a lot of mail at the same time from the same source. So getting within a small amount of time an email, the same email message from the same source, that would be cause for serious concern. You agree with me? Okay. And somehow it's Boharczyk who came up with that simple defense strategy, saying, okay, when you have the same message within a small amount of time on your mail server, just shut down the server, like this. Okay? And he's saying that's like a reasonable defense strategy. Okay, and then Bohacek start plotting some curves. Here we are. And let us take a look at the heavy tail graph. You see, if you look at what's going on, basically the difference in color is the difference created by the defense strategy. And you see that the shape of the curve cannot really change that much by the defense strategy. It seems to be fundamentally depending on the underlying topology. This is the purely random graph. This is the heavy tail. That's a small diameter World Wide Web, and this is the physical graph. Okay, look. Somehow the shape of the curve depends on the underlying graph, not that much on the defense strategy. And then I kind of struggle to come up with some kind of a proof of this. I say, what is happening? How is this happening? And I claim that the delta hyperbolic property, coarse geometry, can give us some kind of an idea as to how to prove this. This is kind of a little bit rough, but this is the idea. Okay. You have G, which is like the logical mail graph. Take it that way. Assume that it's hyperbolic. Now the mail graph, there has been lots of paper that it's heavy-tailed. Hence, by the experiment I did, it seems likely to say that it's delta hyperbolic. Okay. Then you let G prime be the same graph with the defense strategy implemented. Okay? Well, it turns out that if G is delta hyperbolic, the G prime with the defense strategy is also delta hyperbolic. So that defense strategy or not, the propagation is still the propagation typical of a delta hyperbolic graph. And this is the proof. It's based on some concept of coarse geometry. Talking about quasi-isometric embedding, it turns out that the graph G with the defense strategy can be mapped into the graph G without defense strategy by means of a quasi-isometry. A quasi-isometry, it's kind of almost an isometry except for a lambda factor close to 1 and an epsilon not too big. There I have to invoke a big result of coarse geometry saying under a quasi-isometry the delta hyperbolic property is not changed. So that without the defense strategy the propagation is the propagation that we have on the delta hyperbolic graph. With that simple defense strategy it remains the same mode of propagation, still a delta hyperbolic propagation. Maybe with a larger delta, but at least still fundamentally the same mode. And that
That's with this defense.
Yes, with this defense, okay? Because somehow Bohacek came with this curve and it kind of baffled me and I said, what is going on? And I just tried to show the way to build up a theory there. Okay, let me see. Okay, we are getting a little bit, how much longer?
Maybe 10 minutes.
Okay, I'll try to finish in 10 minutes. Okay. All right. Okay, I'd like to go to some other stuff now. Okay, that's going to be a little bit rough maybe, but what I'd like to do now is, as I said, there is another way to do the embedding on a surface with G handles. Okay, any graph has that embedding, and I said this is the gateway to some pretty rough topology. Let me try to give a little bit of the feeling as to what's going on there. Okay, first of all, any graph is embeddable in a sphere with a certain number of handles. Okay. Okay, maybe I'm going to skip that construction. Let me just put it this way. You see, there is a construction based on the rotation system that is systematically finding a surface with a certain number of handles in which you can write the graph without edge crossing. Let's just take that for granted. There is a construction, it's right there, maybe it's messy, where we did implement in C++, it takes some time, but we are getting there. Okay.
I mean,
yeah.
to explain, I mean, if you have a planar graph I can put on a sphere. If I have crossings, then I have to go across.
That's right. That's the idea. Right. That's the idea. And somehow, if you think a bit about that, what's happening?
You have to worry about it.
Yeah. if the graph is really embedded on the surface, you have an ordering of the vertices flowing out of every edge, and that's the whole idea. Conversely, if you have an ordering, you have a surface embedding. Okay, but just keep this in mind. Keep this in mind that if you have the graph really embedded on the surface, you have some way to order up to cyclic permutation the vertices. That's going to be important now. Okay, we are getting there. Okay, it's getting a bit rough in here. Okay. The Alexandrov angle concept. Okay. Okay. Because I really would like to show you that in positive curvature you have really the potential for flooding. Okay, here we go. We have a vertex. This whole graph is embedded in a surface. As a matter of fact, I have some kind of way to order the vertices, the edges flowing out of the graph up to cyclic permutation. Okay, pick a triangle A, B1, C1. Okay, and you have some weight associated with these edges, and then you write what is called the Toponogov comparison triangle. It's basically a triangle in Euclidean geometry, but that is isometric to that one. Now, since we are in Euclidean geometry, you can define an angle there by elementary trigonometry, and that is called the Alexandrov angle. So it's a concept of angle between two edges flowing out of a vertex. Okay, this is pretty simple, but you have to justify all of this. And again, it's like an exercise with the Gauss-Bonnet theorem. But eventually, and then you have to do some limit, but eventually you are getting out of it. Okay, let me just get back to this. Okay, here we go. Here we go. You have a local subgraph there. Okay, you have a vertex and you have its immediate neighbors. Now think about the following. Assume that the sum of the Alexandrov angles, you see right there, is smaller than 2 pi. Okay, so somehow you have like a cone structure there. A cone, you can imagine that you can smooth that over with a sphere, so you have positive curvature there. Okay, if on the other hand the sum of the Alexandrov angle is larger than 2 pi, okay, then you have a fault, and this is negative curvature. Okay, and then look at the very big difference between the behavior. For example, assume that the Alexandrov angle is 60 degrees, which would be the case if you're just counting the number of hops. Okay, in this case, you have 60, 60, 120, 180, 240, it's less than 2 pi, it is like positive curvature. Look at the traffic. Assume the traffic has to go from that node to that node. It's better for the traffic to transit through the base. You are not going to flood that node. But if you have traffic that has to go from that node to that node, okay, you have many nodes connected to that vertex. Instead of making the detour via the base, you'd better go via that vertex. You are going to flood that vertex so that that strong negative curvature is it's a potential for local flooding. And again, you see the curvature concept telling you the nodes that are vulnerable to denial of service attack. Okay. Okay. I have 5 minutes left and I can talk about something fun in here. Actually, I just did this when I was preparing myself in the conference, in the little chat room there. I understand that there is some communication going on in the center. I could see the whiteboard full of communication signal. And this is another application of positive curvature, negative curvature, kind of a fun application. Okay, I'd like to, because we have a pretty good ultra-wideband laboratory, I start talking to some of these people of the ultra-wideband laboratory. And actually you have the same kind of situation in sensor networks, really. Okay, what's happening ultra-wideband? It's basically a signal of very high bandwidth that follows nearly the laws of geometrical optics. And somehow, because ultra-wideband follows the laws of geometric optics, you could have communication when you do not have line of sight. Okay, since it is such a high frequency signal, the out of line of sight communication, for example, between V1 and V4 would be done by bouncing on objects. Like V1 could communicate with V4 by bouncing on that concrete column. Okay, V1 could communicate with V4 by bouncing on that wall. Okay. The same V2 and V3 do not have line of sight communication, but they could communicate by bouncing on that concrete column. They could also communicate by bouncing on that concrete column. Okay. It turns out that we have the same situation as the situation of the Gram matrix. What did I say about the Gram matrix? The story is that you have a certain number of vertices and you have distances among pairs of vertices. And then the Gram matrix is a matrix, and if sign-wise it behaves properly, you have exact isometric embedding. Now this is a good candidate, an excellent candidate for non-Euclidean geometry, because look at the real distance you have in here. So you see, this is certainly not Euclidean. If you look at the set of vertices V1, V2, V3, V4, V5, if you look at the minimum communication cost path, you have to figure out whether this one is minimum or that one is minimum. I don't know exactly which one, but anyway. You have a very good candidate for non-Euclidean geometry. You have a system of vertices, a system of distances among pair of vertices. It's an ideal candidate for non-Euclidean geometry. Okay, then what geometry is it? Is it spherical, hyperbolic, Euclidean? Certainly not Euclidean, because for Euclidean you would need this kind of communication, and you are obstructed by that wall there. Okay, this is the theorem. The theorem is saying that if the obstacles are convex, the geometry is hyperbolic. The geometry is hyperbolic. Then you have what I would say good behavior, in the sense that some of the people dealing with multipath routing are looking at the receptor, and then they are looking at the signal you are getting along different azimuths. Because that's important to have the correct synchronization among all of the channel. The consequence of the hyperbolic geometry is that that relationship, if you look at what you are getting at V3, the strength of the signal, like the quality of the signal versus the azimuth, is going to be a smooth function. Because you remember the stability, the good behavior of the geodesic, somehow the near optimal paths have to be close to the optimal path in hyperbolic geometry, meaning a good quality of the signal versus azimuth relationship. Okay, how do we prove this? Well, that's a very fun exercise. That's why I asked to have some pepper and scotch tape, so I'd like to finish up on a light note. Okay, this is the proof of this. This is the proof. Let me just take 2 sheets of paper and let me cut a round as a model of a convex obstacle. Okay, so I'll have to do this. It's kind of a very elementary topological exercise, and I would like to finish on a kind of a light note. I hope I'm not going to cut my fingers, otherwise it would not be a very good ending. Okay, there we go. Here we go. Okay, so is it convex? Roughly. Okay. So I would like to write a ray bouncing on that column, that concrete column. Okay, and what I'm going to do, if you don't mind, I'm going to write one ray on one sheet and the other ray on the other one. Okay, and you'll see why I'm doing this. Okay, do you agree with me? Do you agree with me? The ray bouncing. Okay. No, I'm taking the scotch tape. It's one of those topological exercises that you easily do in class, in elementary topology, but I think it's going to explain to you a little bit how that proof works. Okay, because I have to glue the 2 cuts together now. Okay. Okay, we are getting there. Okay, a couple of more pieces of scotch tape. and then we'll be there. Okay. Now, okay, I'm separating. I hope it's going to work. Okay, look at this. Let me just put one more piece of tape, and then you might be able to see how it works. I need a piece of tape exactly. Okay, let me just split the sheet. And look at the reflection. Now look at this. It looks like a saddle, doesn't it? You have like going up that way, going down that way. It looks like a saddle, right? You do see the saddle there? Okay, negative curvature. That explains why the propagation is hyperbolic, provided the obstacles are convex. Now, it turns out that the obstacles are nearly convex, like U-shaped. U-shaped. Okay, there we go.
It's true. It's not completely clear where convexity enters the fiction. Basically, you can kind of think about it, but it's not.
The subtle point. If it is not.
Because if
okay, when you do that, you won't get it.
you won't have the saddle.
Locally, at least.
Just take a non-convex obstacle, look at the ray. If you do this, you won't have the saddle, okay? Okay, now if you have like a U-shaped object, it's quasi-convex, then what you could show...
How you say it is.
Huh?
It depends on how you say it is.
A small U-shape, somewhere there. Okay, U there. Put a small U
But
there.
if it is like this building, okay?
Of course not, but put a small U there. Okay, then it can be proved that the geometry is in the large scale hyperbolic with a local patch of positive curvature around the place where the U is. Again, the same idea, a large scale positive curvature. Here it is. This has large-scale negative curvature with, because of the very, very connectedness, there positive curvature inside there. So we are back to the same story in these propagation problems. In case of nearly convex obstacles, you have like negative curvature in the large scale with local patch of positive curvature. Okay, summary. Okay, I said that physical graph, because of their large scale, are negatively curved. The World Wide Web, because of because of the small diameter, is positive. And I'm saying that that concept really encapsulates a lot of trade-offs. Security. Stability requires k smaller than 0. Security, it would mean that you want the geodesic really to go far away geographically from the nominal one to completely caught the enemy by surprise. That would be in positive curvature. The last things I'd like to say, heavy tail or hyperbolic. I have been advertising for hyperbolic. So far, the traditional wisdom has been heavy tailed. Which one is more important? I would say it depends on the application you are targeting. I feel that multipath routing, stability of the network, I think that curvature is relevant. When it comes to self-similarity, packet drop, quality of service, all of these are things that are related to big hubs getting congested. Probably the heavy tail is more relevant. And I think I'm going to stop in here. Thank you.
Thank you very much. We have time for a few questions if you wish.
Yeah, I'm used to you asking me questions. Alaska, Lisbon.
Yeah. So from a very basic point of view, if you look at architecture, a system based on these networks, is there a subtle difference between a distributed architecture or a centralized architecture?
A centralized architecture, that's an architecture where you would have the big hubs. That would be negative curvature. Right?
So
that would be the route map of American Airlines. Okay, or United, the big hubs. Okay, and Southwest Airlines decide on an entirely other route map. That's an interesting observation.
But the metric of the Southwest Airlines is not COPS, it's money. That is different.
yeah, that's a very
Well, it's a success story, Southwest Airlines. So somebody drew my attention on that. He said, go to the web and get the route map of Southwest Airlines.
So the question here is, where is the trade-off? I mean, engineering is about, at the end of the day, trade-offs, right? Security and stability. I mean,
The two are opposites. Because stability would ask stability would require the near optimal path to remain close. Okay, now there is a theorem saying that a near optimal path for a metric is an optimal path for a perturbed metric. Okay, I didn't mention that theorem. So that if you think about a network where you start fiddling with the link weight to do some adaptation, you don't want the geodesics to go too far because you could have the flickering phenomenon, instability. But in that case you have, you see, in that case you have the near optimal path remaining close to the optimal path, so if the enemy knows where the lines are, he might still find his way and tap the signal. Then you would need really the geodesic to go all over the network, and that's typically happening on a spherical space. Okay, so that's like the trade-off.
I have a more modest question here, and that is that I still don't have understanding of stability notion in the following sense.
Okay.
In the nonlinear geometry, at least, when you deal with surfaces, there is classical results about negatively curved surfaces having instability in the sense of roughness of the geodesic flows, right? I mean, nearby geodesics go farther apart. I mean, as you're near triangles. That notion of instability versus the sort of your notion of oscillatory instability.
Okay, now you have to be very careful in
That's
here.
what I wanted to understand.
Okay, because I think what you are alluding to is that in a hyperbolic manifold, if you have two geodesics starting at the same point, they will go diverge, whether they would converge in spherical geometry. Okay, the catch is that you are thinking about two geodesics from the same point from some slightly different initial velocities. I'm talking about geodesic joining 2 points as a whole, and things are going the opposite way then. Okay, you got it. Yeah, it's a catch. It's a catch. Exactly. In GSO 2, and that's a catch, and usually in my class I have to go to that because the students are always confused about that. Okay, we agree.
Any other questions? Okay, we have a round table at what time? We have a round table at 2 o'clock in the conference room, in the small conference room of the center. You're welcome to come. I thought, having a talk that is more on the mathematical, there are people here, and I'm glad that Christian is here, that they're working on different geometry from different aspects, and topology and so on and so forth. And there are others like Carlos and maybe myself are working on this from tomography. So I thought to hear a talk on trying to link these seemingly unrelated things would be of interest to you. Okay, so thanks for coming. Thanks again.
Okay, sure.